facilitate the multi-GPU computation with high efficiency. Okay, the peer-to-peer communications between GPUs must be necessary. Okay, otherwise the efficiency will not be high. Okay, so this is the outline. Okay, yeah. So the basic issues of using the multi-GPUs is for large-scale problems, we need computational resources more than what can be provided by just one GPU. Okay, so yeah, usually I need around 8 GPUs or even more for my larger scale CG computation. Okay, yeah. So for the DGX H100, A100, and V100, they have 8 GPUs on one motherboard. Okay, and this is the most efficient way of using the multi-GPU. And all these GPUs are connected by the NVLink, so the communication would be very efficient. Okay, and the bottleneck, okay, will not be due to the communication, okay, too much. Okay. Okay. So the perfect scenario for using n GPUs is the speed up, okay, divided by number of n GPUs is around 1, even for n much bigger than 1. Okay, it's a ideal scenario, but in reality, okay, as a function of n becomes saturated as some NC, okay, and this NC depends on what kind of problem you are doing and what kind of system, what kind of hardware you have, okay, and such a saturation must exist, okay, depends on just what kind of problem you have and what kind of hardware you have. Okay. Yeah. So after it saturates, then it won't be wise, okay, to increase the number of GPUs, okay, because the speed up, okay, yeah, even you after n bigger than NC, then the speed up turns out to be to decrease rather than increase. So you are wasting the resources, okay, by increasing the number of NC, okay. So yeah, I would think, okay, if you look at the speed up divided by n, and when, yeah, it will not be equal to 1, okay, but it's getting too small than 1, say less than 0.8, then I think it's not justified to use more GPUs, okay, as n is increased. Okay. So the reason the speed up cannot linearly increase with respect to n, okay, yeah, it's because the bandwidth for the data computations, okay. So the data communication has a fixed bandwidth, okay, and the bandwidth cannot be matched with the number of GPUs, okay. Yeah, when the number of GPUs are increasing, the access of the data, okay, or the bandwidth required to efficient data communication is higher, okay. So that's reason why, because of limited bandwidth, then yeah, the bottleneck is in the data communications, okay, rather than the speed of the GPU. Okay. So so far, okay, for the multi GPU systems, okay, the best solution is to use the NVIDIA NVLink, okay. So NVIDIA NVLink, okay, is specially designed for the communication between any two NVIDIA GPUs, okay, yeah. So now the third generation of the NVLink is can be up to 900 gigabytes per second, okay. So the first generation is 300, the second generation is 600, and 900 gigabytes per second is the third generation, and so far is the fastest, okay. Yeah, this NVLink can connect all GPUs on the same motherboard, but it only applicable to the NVIDIA GPUs, say H100, A100, and B100. And also these are RTX 3090 and RTX 2080 Ti, etc. Okay, so not too many NVIDIA GPUs uh, can can be uh, can be connected by the NVLink. Okay, yeah. So, for example, for the DGX V100, okay, then you can see, okay, there are 8 GPUs, okay, and these are the NVLinks, okay, yeah, and these lines between the GPUs are the NVLinks, okay. So this for the V100, okay, yeah, it can have the NVLink 2.0 and the data rate is around 300 gigabytes per second, okay, yeah. For the DGX A100, okay, and there's an NVLink 3.3 generation, and the total data rate is around 600 gigabytes per second. Okay. So again, it has 8 GPUs on the same motherboard. Okay. For the system, okay, you can use, okay, yeah, in this class, okay, is a 2 GTX 1060 on the PCI bus, PCIe bus, okay. And the PCI is 3.0, okay, not the latest one, okay. It's an old motherboard, okay. And the data rate is around 30 gigabytes per second, okay. So you can see, okay, for this motherboard, the data communication is around 10 times less than the NVLink, okay. So NVLink is really crucial, okay, for the multi GPUs. Okay. Now you look at the device query, okay. Then you see, okay, it says the peer access from the GPU 0 to GPU 1, and vice versa from the GPU 1 to GPU 0, okay. So in this case, okay, that means they can peer to peer access, okay, from one GPU to another, okay, and without going through the CPU at all, okay. So these are most essential features for the using the multi GPU, okay, via the PCIe bus. Okay, yeah. Any questions so far? No. Okay. Further with the multi GPU, how do we decide the code? Okay, yeah, change the code. Okay, yeah. So there are many different ways of doing it. Okay, but I think the most viable way is that using the OpenMP. Okay, so and with one OpenMP thread, okay, handling one GPU. Okay, so under the OpenMP, I can create M threads. Okay, and then if I have M GPUs, then each thread control the execution of one GPU. Okay, so before, okay, we only have using one thread from the CPU, okay, to control one GPU. Okay, now I'm using OpenMP to create M threads to control M GPUs. Okay, so it's a rather straightforward generalization. So let me look at the vector addition. Okay, again, but now with the multi GPUs. Okay. So I partition the vector into M partitions. Okay, yeah. So vector. Okay. Now, if for one GPU, I have to do all or using the threads. Okay, of one GPU to do all the addition. Okay. But now since I have M GPUs, okay, I can partition the vector, okay, such that, okay, this portion of vector elements go to the GPU 0. And then, yeah, so this one of this, okay, is this portion, okay, is handled by the GPU 0, okay, and so on, okay, up to the GPU M minus 1. So in this way, okay, the computation will be ideally, okay, could be increased by, I mean, speed is increased by factor M, okay? Yeah, so the speed up, okay, with using M GPU would be M, okay? Yeah, but in reality, okay, if your computation requires the communication of data between different GPUs, then the speed up will not be perfect, okay? Yeah, for this case, okay, it should be ideal because for this vector addition, okay, the computation doing by the GPU 0, okay, are independent from any other GPU's computation, okay? So the speed up will be more or less ideal, okay? Yeah, because there's no communication between the GPUs in this case. Okay. Later, I would discuss this solve the Laplace equation. Then in that case, okay, it requires the data communication between the GPUs when they go to the boundaries of different region handled by different GPUs. Okay, yeah. So let me talk about this vector addition first. So I use the OpenMP create M threads, and each thread, okay, control the one GPU, and this one GPU just doing the vector addition of a portion, okay, of a partition of the vector. Okay, so yeah. In general, okay, the template of using multi-GPUs with OpenMP is the following. Okay, yeah. First, I have to declare there's a header of the OpenMP omp.h. Okay, and then in the main code, okay, yeah, I have to set the OpenMP number threads. Okay, how many threads you need? Okay, so I set the number of threads to equal to the number of GPUs and GPUs. Okay, so set the number of threads is equal to number of GPUs, and then start of the OpenMP. So so this syntax, okay, is always fixed. Okay, you must use this syntax. Okay, PAMA OMP parallel private, and CPU thread ID. Okay, so with this, so different threads will using the different thread ID. Okay, so each thread will compute differently according to its CPU thread ID. And since the CPU thread ID, okay, each CPU thread, okay, control different GPUs. So different GPUs is doing its own commutation. Okay, yeah. So in the code here, there's CPU thread ID is OpenMP get the thread number. Okay, so each thread gets its own ID. Okay, and then after it gets the CPU thread ID, then it set the CUDA device. Okay, to this CPU thread ID. So set the device number. So in this case, okay, this would select the device. Okay, for the computation. Okay, which depends on the ID. Okay. Then each thread on the code with its own CPU thread ID. Okay. So then there's a computation here, and then so this is the same thing. Okay. Yeah. Any questions so far? No. Yeah. If you have any questions, you can turn on your microphone and then ask the question. Okay, you can interrupt me anytime. Okay, and also turn on your camera. Okay, so that I can see you. So this is the code. Okay, of the vector addition with multi GPUs. Okay. So this is a code fragment. Okay, I will show you the entire code later. Okay. So this code fragment just to outline the essential features of the vector addition with multi GPUs. So again, you have to just set the number of the OpenMP threads equal to the number of GPUs. Okay, and then the CPU thread ID. Okay, yeah, get the CPU thread ID. Okay, from using this command, and then set the device. Okay, CUDA set device with this CPU thread ID. So in this case, I set the device number equal to the CPU thread ID. Okay, I think this is the most convenient way of, okay, so you will not confuse yourself. Okay, but of course you can set the device number different from the CPU thread ID. Okay, as long as you know what you're trying to do. Okay, so now then I CUDA malloc. Okay, so the size of the vector is this. Okay, since I have n GPUs, so each GPU only has to handle 1/n of the size of data. So you see, yeah. So this is the device vector. Okay, yeah, allocate device vector, but with only the size. Okay, not the entire size of the vector A, but only 1/n of the size. Okay, yeah. So the size divided by the number of GPUs. Okay, for the device vector A, B, and C. Okay, and then copy the vectors from the host memory to the device memory. So in this case, okay, each GPU, okay, each thread, okay, is doing the copy. Okay, so so each thread, okay, copy a portion of the vectors, device vector, to each GPU ID device. Okay. So you see this CUDA memory copy. Okay. Yeah, from this host vector. Okay. Now this is the location of the array. Okay, according to which CPU thread ID. Okay. So you see, this is the HA. Okay. Yeah, is the initial address of the host vector A, and then I pass this. Okay, n divide by that, and then times the CPU thread ID. Okay. So so that means if this locates to the give the address. Okay, of the device vector of the host vector A. Okay, which corresponding to that partition. Okay, goes to the device vector of the A in the GPU. Okay, with the CPU thread ID. Okay, its own CPU thread ID. Okay. So if you CPU thread ID, suppose you have 2. Okay, then the CPU thread ID is from 0 and 1. Okay. So that means if for the one with the CPU thread ID equal to 1, then it will start from the address, which is exactly halfway of the entire HA address. Okay, size of it. Okay, so the initial address plus the half size of the vector. Okay, yeah. So then the size of the vector, okay, transferred from host to device is again is the size divided by the number of GPUs. Okay, so this is the similarly for the B. Okay, is the case. Okay? Yeah. Okay. Now,
excuse.
Then you can execute the kernel. Okay, the vector addition. Okay. So then the blocks, the grid. Okay, the how many blocks of this grid, and then how many threads per each fault thing. And then the DA, DB, DC. So each device will do the vector addition, okay, of each partition, okay, of the vector, okay. So get the device vector. And then the size, okay, what's the size of the vector is the n divided by the number of GPUs.
Excuse me, teacher.
So after each GPU has finished its operation, then synchronize it, okay? And then copy the results from device memory to the host memory, okay? Then the HC, okay, contain the resulting vector in the host memory, okay? You see, when it copies, okay, each GPU, okay, copies the results to different address, okay, according to each CPU thread ID, okay? Okay. So you have the n, okay, n is the how many the size, okay, divide divided by the number of GPUs, and then times the CPU thread ID, okay, and then this is the size over the n, okay, n GPUs, okay. So after each thread, okay, copy its results to the corresponding address of the host vector HC, and then the HC, okay, can contains results, the entire results of the vector addition, okay. Any questions about the code?
Excuse me, what is
Yes.
the difference between size and the capital N?
Size, I think it's better. I go to the code, okay, you will see more clearly, okay, the complete code, okay, this is only the fragment, okay, so let me go to the code, okay. Let me, I think you already covered it, okay. Let me see the connection, okay, okay, let me share the screen, okay. Let me see. Let me stop the slides okay, and then share the screen for the terminal, okay. Okay, now. The terminal seems okay. So this is the device code, okay. Actually, the device code is the same as before, okay. Same as the one GPU, okay. So this is the vector addition, and then the device, okay, and then the memory, okay. So number of GPUs, okay, and the device, okay, the device number, okay. Actually, this is the same as the number of GPUs, okay. So the size, okay, So the GPU, and then you can assign the device number, okay. The device this array, okay, contains the device number, okay, and which is the you can arrange it, okay, in any order you like, okay, actually, not necessary to be equal to the I, okay, device I, the array, okay, not necessarily equal to the integer I. So size is the how large, okay, of the vector, okay. So this is the size n, okay, the size of the vector, okay. Yeah, and the size is the size, okay, how many how many folds, okay, the size of how many bytes, okay, how many, yeah, so yeah. So this is the difference between size and n, okay, you see? Yeah, so this answers your question. Okay. Then choose the yeah, the flat blocks, the flat size. That means the block size and the grid size. Okay. Yeah. So this is the what you have already seen before. Okay. Yeah. And here this is the for the testing. Okay, whether the memory okay has a sufficient memory. Okay. Yeah, for the 6 GB. Okay. Yeah. Yeah. Here I have to emphasize this. Okay. The CUDA event create. Okay. The event must be created after devices are set. Okay. So you cannot declare the CUDA events for timer at this stage. Okay. Yeah. So if you declare this at here, okay, then the timer may not function well correctly. Okay. So yeah. So after device are set, okay, then you can create the event. This is for the OpenMP, okay? For the, if you do not use the OpenMP, then it won't be a problem, okay? If you declare the CUDA event create, okay, declare at this step, okay? So here, I use the CUDA set device, okay? It's according to the DEV, this array of the CPU fat ID, not necessarily the same as the CPU fat ID, okay? Yeah. So this is just a mapping, okay, rather than using the CPU, the device number is equal to the CPU fat ID, okay? Yeah. But anyway, this is just a minor variation, okay? Yeah. So yeah, this CPU fat ID is equal, I used OpenMP get the fat number, okay, fat ID, okay, so get the CPU fat ID, okay. And after this is set, after this CUDA set device, then I can start the timer, okay. I cannot start the timer here, okay. Only after the device are set, then I can start the timer, okay. Yeah, otherwise you will not get the correct timing, okay. And then now I allocate the device vector, okay. Yeah. So you see each GPU, okay, only handle a partition of the vector. So the size, okay, how many bytes, okay, is not the total size, okay, but the size divided by the number of GPUs. Okay. Okay. Then copy the vectors from the host memory to the device memory. Okay. Again, okay, the copy is only just a partition of the host vector and the partition of the HA and HE, okay, okay, from the host memory to the device memory, okay. So the size is the size of the vector, okay. I mean, how many bytes is the size over the number of GPUs, okay. Yeah. So the CPU frame ID, okay, yeah, is play a crucial role here, okay. It would identify the correct partition. Okay, so this gives you the correct address of the partition. Okay, of the vector in the memory should be copied to the device memory. Okay, yeah. So at this stage, I stop the timer. Just try to time how long it takes to the data, okay, from the host to device. Okay. Now in this case, since the copy, okay, is only a partition of the vector, so the time must be smaller. Okay. That means if I'm using multi GPUs, then the input time will be a factor n GPUs, okay, less, okay, because the size of vector is simultaneous there, n copies, okay, going on simultaneously. So it becomes more efficient, okay. Yeah, as long as the bus, okay, the yeah the PCIe bus, okay, can handle, you will not, can handle such a traffic, okay, then the copy will be n times faster. Okay, that means if the vector is not too large, okay, in that case, yeah, then using n GPUs, okay, would be much faster than just one GPU. Okay, using one FET, using n FET, okay, is faster than just using one FET to do the copy. Okay, yeah. And in this case, the different FETs, okay, copy the data from the host to the different device, different GPUs. So this gives the input time for the GPU. And then I will start the timer for the computation, okay, for the kernel, vector addition kernel. So in this case, I just select the CPU for ID, okay, 0, okay, or do the timing for the computation. Okay, I do not go through different GPUs and get how much the kernel it take, how much which GPU takes how much time. Okay, in this case, I assume they are more or less the same. Okay, so and then stop the timer here. Yeah, the terminal is response a little bit slow. Okay, so then this is give me the processing time for the GPU, and also I can compute the GPU gigaflops. Okay, yeah, and after the computation, then I can transfer the result, okay, from the DC, okay, to HC, okay. Then the DC, okay, the result, okay, and then it should be going to the corresponding partition or the address, okay, in the host vector, okay. So this the XC plus this offset, okay, yeah, such that it will go to the correct position. Okay. Yeah. Again, the size is just what is the size of each GPU, okay, the DC of each GPU, okay, yeah. So after copy, okay, then we can feed the device vector in the GPU, okay, because this result, okay, this DA, DB, and DC is no longer used for another kernel, okay, so it can be feed, okay. So the stop the timer, and then the computer output time, data output time for the GPU. So and then I can compute the total GPU time. And now I can start the timer for the CPU computation, compute the reference solution, okay, using the CPU, and then do the same computation, and then finally I can compare the results and compare the speed, okay, the time, okay, for the CPU and the GPU, okay, and then and get the speed up, okay, of the GPU, okay. So and also check the results. Okay. Yeah. So so you can see the code, okay, is more or less similar, quite similar to the vector addition of one GPU. Okay. but the essential difference are the using the OpenMP, and each thread, okay, control one GPU, and each GPU only doing equal partition of the data of the computation. Okay, so this gives me the speed up. Okay. Yeah. So now let me run this code and see how it works. Okay, how does the two GPU perform compared to the one GPU? So I use two different inputs. Okay, yeah, one GPU input here. Okay, just one here, and then the device number is allocated by the condo. Okay, so GPU ID here, and then the vector length, okay, is 2 to the power 27. Okay. So this is the number, okay, 2 to the power 27. And the block size is 32. And so you can assign different block size, okay, but in this case, okay, yeah, I think 32, okay, is not too much different from other block sizes, okay. Yeah, I think it's large enough, okay, to give you the good performance, okay. Okay. You see the terminal response is quite slow. Okay. To GPU. Okay. So here, the input file is this, the number of GPUs and the device number. Okay, I just end the device number 0 and 1. Okay. Yeah. Okay. Now, let me look at the CMD file. Okay, this job description file. Okay. So you see. Here, the required CPU is the required GPUs, okay, here. But yeah, for one GPU, then you should put one. But now if you have used two GPUs, then you should put two, okay. But now the job description system, okay, already, I mean the CMD, I mean the condo, okay, I already changed it so that when I have the device number 0, 0 and 1, okay, and then it automatically, okay, change the number of GPUs to 2, okay, yeah. And okay, here is the full path of the working directory, okay. You can type PWD, okay, and then you look at this, whether this is the same as the what is the line here, okay. If not, then your CMD will not work, okay. So then yeah, somehow it's stuck, okay, here. Okay, now here the argument here, okay, I can enter this input 1 GPU or input 2 GPU, then I submit twice, okay, submit once with this and then the second time with this, okay. But now the CMD file can accommodate this, okay. This is the command vector at NGPU, and then there's a two input file, okay. So you would use one input file, okay, to do the computation, and then use this input file, 2 GPU input, okay, to do another computation, submit another computation, okay, and all outputs is go through here, okay. So the input file, okay, can be just one or can be more than one, okay, yeah. So now you see, it takes some time to respond, okay. Maybe the internet connection now is not very good, okay. Yeah, so now Control, submit. You see, it echo, it responds very slow. Control, submit. CMP. Okay. Yeah, only today, okay, it is going so slow, okay. Before, okay, it was very fast. I don't know why. So they will just see, so now it's initialized, okay, and then you will be running soon, okay. Yeah. Okay, now it's done. Okay. So let me see. Okay, now, so this is the output, okay, just obtained. Okay, and this output O is the one which I have done several hours or 4 hours ago. Okay, so let me get the output file. Okay, now. So the first portion is the result of the one GPU. Okay, so you can see the number of GPUs one. Okay, and then the input data input time, and then the processing time, and the GPU gigaflops, and the data output time for GPUs. Okay, so this is for the one GPU. Okay, and for the CPU, okay, it's 611 millisecond. So in this case, the GPU speed up is about 1.4. Okay, and the result is yeah, the same. Okay, yeah, CPU and GPU result is the same. Okay. Now, if I repeat the computation, okay, with two GPUs, then you can see, okay, the number of blocks, okay, that means the number of blocks of one GPU, okay, is half of the number of the one GPU. You see, yeah, the block size, okay, is 32. Okay, this is the grid size. Okay, yeah. So because there's the grid, the number of blocks, okay, is divided by 2. Okay, if I have two GPUs. Okay, yeah, and yeah, because the size of the partition of the vector handled by each GPU is half of the entire vector. Okay. Now, for the data input time, because the size of the vector is decreased by factor 2, so yeah, input time seems, yeah, for each GPU. Okay, let's see the input time. So this is the more or less the same. Okay, you see, yeah. So that means using too fast to read the data. Okay, yeah, more or less the same. Actually, this one seems using two GPU. Okay, seems even a little bit slower. Okay, yeah, but this is a fluctuation. Okay, but processing time is really different. Okay, this 32 and this 16. Okay, so the processing time, okay, is just one half. Okay, yeah, and of course the gigaflops, okay, is the 24.8. Yeah, in this case, okay, because I have the two GPUs, so the time, okay, is yeah, just factor 2, okay, factor of 1/2, okay, divided by 2, okay, yeah. And the data output time, okay, you can see the data output time is really reduced almost by factor 2, okay, yeah. So this is 136 millisecond, and this is the 245, okay, so, and the data output time, okay, and then the total time, of course, okay, is for one GPU, okay, is yeah, small, okay, much small, okay. And for the processing time for the CPU is more or less the same as before, okay. And the speed up, okay, is the total time for GPU, okay, and this is the processing time for the CPU, okay, the ratio, okay, compared to the ratio of these two, okay, then the speed up is around 1.958, okay. So compared to the 1.411, yeah, so yeah, it's not a factor 2, okay, yeah, so speed up, okay, is 1.4, then you should expect this is 2.8, okay. The reason is the I/O time, okay, yeah, only the processing time is a factor 2 faster, okay, but the I/O, okay, is cannot, the input time, okay, yeah, is not reduced by factor 2, but the output time, the data output time is reduced by factor 2, okay, so yeah. So this is the using 2 GPU, okay, to do the vector addition, okay, yeah. Any questions? Yeah.
老师，我想要问一下，在你的程式码第132行当中有一个Prama OMP barrier， 这是什么意思
？Yeah，其实嘛，我看看啊，我先要离开这个，我这边这个 terminal 好像 OK 不太 OK 好，我要 go to a code OK， you see the response OK not too good OK but yeah 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 right you're asking this right？
对，我要问的是第132行。
啊，你可以大声一点，我听不到。
第132行。
132行，是几行对的？是几行
？132。
我没有看到那个 number，OK。
就是再往下一点。
是哪行？
到 memory 到 CUDA memo 那个 memory copy 那边。
哦 ，CUDA memory copy，OK，yeah。
对，底下有一个 OMP barrier。
OK here， you're talking this。
上面一点。
CUDA memory copy。
上面一点。
大一点，
过头了。
Here，
对。
这边这里，就是这里啊。
对，下面有一个那个 OMP barrier， 这是什么意思？
哦，Prama OMP barrier，OK，yeah，yeah. So this is the try to make sure all the threads, okay, complete this operation before going on, okay, yeah. You see, yeah, Yeah, this is the each thread, okay, is doing the memory copy, okay. But in some of the, for this code, okay, it doesn't matter which processor, okay. Yeah, I mean, all the computation in each GPU, okay, are quite independent for this vector addition, okay. But in some other cases, okay, the computation, okay, yeah, is one GPU, okay, may need to access the data of another GPU. Then in that case, okay, it's crucial to have all the GPUs, okay, ready, okay, finish this operation before proceed, okay. So this is a barrier such that more or less like the synchronize all the flash, okay, operation, okay. Yeah.
Okay.
After this, all the data are copied to each GPU, and each GPU finish this copy operation. Then they start the computation. Okay. So this is the barrier. Okay. So this is the primitive. Okay, for the OpenMP. Okay. Yeah. Yeah.
OK， 谢谢老师。
Okay. Okay. Any other questions? Yeah. Yeah. This is an important question. Okay. Yeah. Yeah, in general, okay, yeah, such a barrier should be set. Otherwise, the computation, there will be some confusion between the operation of each thread, and then you may get a wrong result, okay, if not the threads are not all synchronized, okay, or so, yeah, it should be put a barrier here, yeah. In general, okay, but for this vector addition, okay, this barrier actually is not essential. Any other questions?
Well, I have a side comment.
Yeah.
This is Yu Wei. So to see the line number in the editor, you can simply type column followed by set number.
Okay, okay.
Yeah, and the set
column number. Okay.
Yeah. No, not column number, but simply number.
Oh, set number. I see.
For unused.
Okay, thank you.
And enter.
Let's see.
Yeah.
Okay, okay, good. Thank you. Okay.
And
yeah.
by the way, if you want to move to specific line, you can type column followed by the line number. For example, you type column and 130. Column.
I think I can just do this. Okay.
Right? Yeah. Yes. Exactly.
I don't need the column. Okay. Yeah. So right.
Yeah.
Okay, so this also will. This is usually what I do. Okay, yeah. Okay.
Yeah.
Anyway, thanks for pointing this out.
No problem. I have one minor question regarding the processing time of for the 2 GPU. It looks like the reduction in time is basically related to the total size that we used for the computation. Like in line 128, size divided by n GPU. So the acceleration of the speed mainly come from the reduction of the size, right?
Yes.
Okay. Thanks.
Yes.
To confirm. Thank you.
Okay. Yes. Yeah. Reduction of size and also the reduce the amount of computation. Okay. Okay, by a factor of 2. Okay. In this case, so the processing time is reduced, and the output data output time is reduced almost not exactly the factor of 2, but somehow the input data input time, okay, is not reduced so much. Okay, I don't know. Let me look at my old. Yeah, because this may. Let me look at the old output. Okay. Output. Okay. You see, data input time here is for the 2 GPU is 139.7 millisecond. And for this one is 154. Okay, so a slightly faster, not a factor of 2. Okay, but in the output over here, somehow this is the okay. Okay. For this one, okay, you see, for 2 GPU, even a little bit faster, a little slower, okay, than the 1 GPU. So, but I think the size of vector in this case actually not too large. So I don't know, the fluctuation seems, but for the output, okay, data output time actually is reduced, okay. Yeah, almost a factor of 2, okay, by reduced a factor of 2. Yeah. So, but for the processing time is definitely, okay, reduced by a factor of 2, okay, in the case of the for the 2 GPU, because the number of operations, okay, yeah, is less, okay, for each GPU. Yeah.
Okay, thank you.
Okay. Let me return to the lectures, okay, lecture slide, okay. Yeah. Let me see. Okay. Okay, let me stop sharing this screen and then back to another. Let's see. This one, I think. Yeah. Okay. So, now, besides the vector addition, also solve problem, say the Laplace equation, okay, with 1 GPU. Now, we can also solve the Laplace equation with multi GPUs, okay. In this case, okay, then it requires the communication between the GPUs, okay, yeah, because some of the data is stored in another GPU, okay. So when the GPU has to access the data, okay, from another GPU in order to proceed with the computation, okay. Yeah, this happens, okay. Yeah, say for example, I have 2 GPUs. So I partition this data into 2 portions, okay, say upper part and lower part. Okay, so the upper 5, okay, 5 times 10, okay, is for GPU 1, and then this for GPU 0, okay. But when I come to this point, when the GPU 0 come to this point here, and the updating of the 5 at this point requires the average of these labels, okay. And one of the labels is in the device the data is in the device memory of another GPU. So the GPU 0 has to get this data, okay? Vice versa, okay, vice versa, okay, for the GPU 1, okay, when it comes to this point, okay, and then to update this point, the file here, and then it takes the average as an average of these labels, okay? And this label, okay, is in the GPU 0, okay? So it has to get this data from GPU 0, okay? So it's essential, okay, the GPUs, okay, can access the device memory of another GPU, okay? So this is called peer-to-peer, okay, communication, okay? So in this case, this is the communication, data communication between the GPUs, okay? And these GPUs are called peers, okay? Yeah, yeah, they are peers to each other, okay? Yeah. So if the data cannot be assessed directly, then the computation will be a bottleneck. When it comes to the boundary. And then the computation will be much slow. Due to this access of data from another GPU. So for this GTX 1060, it can access the data from its peer from another GPU, through the PCIe bus. So this called so now we have a 2 GPU, and then this is the device memory of the GPU 0, and this is the device memory of GPU 1, and then these 2 GPU cards are put on the PCIe bus. So so this is the device memory, of the GPU 0, and this is the device memory of GPU 1. So now the GPU 0, can access the data from the GPU 1 memory. And also we can copy the data. Not only just read, but copy the data from the GPU 0 to GPU 1 and vice versa. So not only access, not only read, but also write. Write the data from the GPU 0 device memory to the device memory of GPU 1. And this operation, this no matter read or write of operation, can be done directly, through the PCIe bus without the intervention of CPU. That means CPU has nothing to participate, in this operation. So this is the fastest way of. So the peer-to-peer communication between GPUs is essential, for the multi-GPU computation. And of course, the fastest way, to do the communication between GPU is through this NVLink, as I showed you in the beginning. So this is the NVLink, the NVLink, So this is the special device, the connector, made by NVIDIA, such that the communication between the GPUs could be as fast as possible without go through the PCIe bus, without the limitation by the PCI bus. So this is much faster than the PCIe bus. So for the first, for this memory copy, first I have to check whether the device can access the peers. For the GTX 1060, we know, this is possible. So whether can access from 0 to 1, GPU 0 to GPU 1, or GPU 1 to GPU 0, and then we have to enable the set device, enable set the device, enable device 0, and then could the device enable peer access. You see, in the beta edition, we don't need to access the data from the peer, so we did not enable the peer access. But for the Laplace equation, we have to use this command, could this device enable the peer access. And also the GPU 1, 0. So so this is the enable the device 0 such that it can be peer can access it. And for the GPU 1, I can do the same. And perform the peer peer-to-peer memory copy, okay, is just the CUDA memory copy device to device, okay. So you see, before we only look at the host to device or device host. Now we also have the device to device directly, okay? Yeah. So this is from GPU 0 to GPU 1, okay, and with the size, okay, yeah. And we can shut down the peer-to-peer at the end, okay, so disable the peer access, okay, yeah. Okay. Okay. Now, I think it's better to go to the example here, okay, yeah, so this is the simple kernel, okay? And the simple kernel is the copy the data from source to the destination, okay? So this is the simple kernel, very simple kernel. So that's destination, the yeah, equal to the source, okay? Yeah, so this is copy. So for this, okay, is the direct access, okay, is the, yeah, first I set the device to the GPU ID 0, okay, so, and then execute this simple kernel, okay. Then this will write, okay, from the GPU 0, okay, to GPU 1, okay, yeah. And now if I set the CUDA device, again, I set the device to GPU ID 0, okay, and execute this again. But now with the source is the GPU 1, okay, then you will read from the GPU 1 to GPU 0, okay. So this is a write to the GPU 1, okay. This is read from the GPU 1 to GPU 0, okay. So yeah. So you have set the device 1 here, then this is, yeah, this is a read from the GPU 0, okay, from here to read from here, okay. And this is the write to the GPU 1, GPU 0, okay, write to the GPU 0, okay. So it's easy, okay, to understand, okay. Yeah. After such a then we the peer-to-peer, okay. Yeah, so at the end, okay, at the end, then we will shut down the peer-to-peer. So that is the same as before, okay. Yeah, so this is the disable, okay. Yeah, so yeah, disable the peer-to-peer, okay. Yeah. So with this enable, okay, then we can, yeah, use this peer-to-peer access to do the to solve the Laplace equation with 2 GPUs, okay. And in that case, you will see the speed up, okay, with the peer-to-peer access, okay, yeah, will be greatly enhanced, okay, yeah. Not a perfect tool, okay, because the PCI bus, okay, is not so fast, okay. So yeah, you may see as if the ladder size getting larger, then the speed up will be getting higher, okay, but you will never reach to perfect 2, okay. Yeah, if you have a 2 GPU, the speed up will not be 2, okay, but you could up to say 1.8 or so, okay. Yeah. So next time, okay, I'm going to talk about the how to solve Laplace equation with 2 GPUs, okay. Any questions about the peer-to-peer? No? Yeah, I think next time you will see in more details of how to use the peer-to-peer operation, the data transfer, and then the read and write, okay? Yeah.
Professor?
Yes.
So if we want to do inner product, we will have to do peer-to-peer activation too.
If you want to do what?
Inner product.
Oh, inner product. Okay, so there's the problem set. Okay, yeah, there's in the problem set. Yeah. So in the inner product, okay, it doesn't need the peer-to-peer. Okay.
Oh, okay.
In the inner product, you only need the parallel reduction, and the parallel reduction is within one block. Okay, and this is within one GPU. Okay, it doesn't require access to get the data from another GPU. Okay. Because you would never split one block into two GPUs. Okay. One block must be accommodated in one GPU rather than split into two GPUs. Okay. So,
Okay. I see. Thank you.
Yeah. Any other questions? Yeah. Let's see. Last time, okay. Actually, there's some one topic I have no time to cover at that time. So that was the texture memory. Okay. So now I have some time so I can go over it. Okay, about the texture memory. Okay, and there's a sample code. Okay, for the texture memory. Yeah. So the Laplace equation, solve the Laplace equation using texture memory. Yeah. I think now the GPU code, that the GPU hardware, okay, has been improved a lot. Okay, so seems to me, okay, using texture or not using texture does not make too much difference. Okay, in the performance. Okay, but for the old GPUs, okay, using texture may enhance the performance because the reading the data, okay, through the texture, okay, it would be much faster. Okay, so let me talk about the texture. Okay. So the texture memory. Okay. So the texture memory can be regarded as just the read-only cache. Okay. So only read through the texture. Okay, but you do not write to it. Okay. Yeah. You also always write to the device memory. Okay. But when you read the data from the device memory, if it's through the texture, then for some special type of data and the texture, this texture through the reading through the texture memory will be much faster than just reading from the device memory. Okay. So for some data which is local, physically, okay, the local region of the physical space-time, but they are separated far apart in the linear memory. Okay, you see, for example, the 5xy, okay, and the 5xy plus 1, okay. Yeah, physically, okay, these two phi are at the label, okay, their label, okay, y plus 1 and y, okay. So they are labels in the physical space, okay. But in the memory, okay, because this is a linear memory, okay, the mapping, okay. So they are in the position, okay, for the xy is in this position, okay. But for this point, xy plus 1, is in this position here. So it's separation by nx, okay. Now, if nx is very large, then they are separated quite far away, okay. So but in your computation, say for example the Laplace equation, you need the labels update using the average of the label. Okay, so they are labels, but they are not labels in the linear memory. So to access them may take some of the labels. Okay, may take longer time because they are not in labels in the linear memory. Okay, even though they are labeled in the local in the physical space. Okay. So the texture in this case, okay, turns out to be useful. Okay, yeah. So yeah. You see, this example is quite often happens in physics, in physical science and engineering, because all physical laws are local in the space-time. Okay, and the reason is local because this equation, these fundamental laws of physics, okay, most are written in terms of the partial differential equations. Say, for example, Maxwell equation, Schrödinger equation. They are partial differential equations, and they have the derivatives, and the derivatives are always related to the labels, okay? Because the finite difference, in this case, the finite difference is the label, the finite difference of these labeling values, okay, in the physical space-time, okay? So the textual memory are useful to optimize the CUDA code, okay, in science and engineering, okay, because the textual memory, okay, would take into account the locality such that when you assess the data, okay, in physical, in the of the labels of in the physical space, then you will faster than you just reading it from the linear memory, okay, okay. So that's the disadvantage of using the textual memory, okay. But as I said, okay, as NVIDIA, okay, the newer generation, the new latest NVIDIA GPU, okay, they may have already built in some hardware, okay, and even though you assess the data, okay, then it may already sufficiently fast, okay, yeah, and in that case, okay, using textual memory or not using textual memory, okay, actually might not make too much difference. You can always test, okay, whether using textual memory can enhance the performance a lot, okay. So yes.
Professor, so
Yes.
so texture memory just collect the local information.
No. Textual memory is that okay. You have the device memory, and then a portion of device memory bound to the texture. Then you can either access the data from the device memory directly or through the texture. Okay, so texture is only the cache, only a cache. Okay.
Oh, okay.
So you can regard it as a cache. Okay, it's not anything additional. Okay. Yeah.
So I don't know why it can access the memory about around the local memory faster than
Yeah. This is the design. Okay, this is the hardware design by the NVIDIA. Okay. Yeah,
Oh,
I
okay.
think if you want to know the details, okay, how they attain such a, the enhancement, okay, then you have to look into the user's guide or the menu, okay, yeah. So I don't know how they did it, okay, or to what extent, okay, they can do it, okay, yeah. I think this is some kind of hardware, okay, and how can they take into account of the locality, okay, yeah, because the hierarchy, okay, yeah, they have some hierarchy there, okay, built inside, and this hierarchy, okay, can take care of the locality, but such a hierarchy, okay, cannot be perfect, okay, yeah. So you see for the video, okay, okay, it also has to deal with some locality, physical locality, okay, yeah, and I think that's the underlying reason why they developed this texture memory in order to enhance the performance, okay, when reading the data, okay, yeah. So I can imagine it's natural to develop this texture memory, okay, but
Okay.
the new underlying algorithm, okay, I don't know, okay.
Okay. Thank you.
Yeah. Yeah. Okay. But anyway, you can test, okay, how quick is the performance of the using the texture memory. Okay, but first, okay, let me tell you how to set up the texture. Okay, yeah. So the texture. Okay, this the sample code here. Okay, yeah, you can look up this Laplace text. Okay, and this Laplace text.cu. Okay, and so this is how set up the texture is this. Okay, yeah. So this is rather looks complicated. Okay, yeah. Yeah, but you have to this just the syntax. Okay, you want to know all the details, you have to look up the user's guide or the menu. Okay, but I point out the crucial things here. There's in the color. Okay, so you have the for the Laplace equation. Okay, you have the two array. Okay, and old and new. Okay, and they're in the device memory. Okay, now you want to read this array through the texture, then you have to declare this texture, old texture, new, old text new. Okay, yeah. So this is the CUDA texture object T. Okay, so this declare this two array is a texture in CUDA. Okay. So now here, so this is the device. Oh, okay. So this is the linear memory, in device memory. Okay, yeah. So now I have to create the texture object texture. Oh, okay, yeah. And then I have to do the same. Okay, for the text new. Okay, text new. Okay, which is with the d new. Okay, yeah. So so this is the set up the texture. Okay. So in order to get the data, okay, from through this texture cache, okay, text O and text new. Okay. Yeah. So after set up the texture, then I can do this execute this kernel, okay, with the d new and do. Okay. Okay. Now in the kernel, okay, in the Laplace, okay, here. In doing the Laplace, okay, then we have to get the say the update, okay, the bottom, top, left, and right, okay. So we have to get the DO, okay. But instead of getting DO from the device memory, I get this data from tab O, okay. So there's from the texture, okay, okay. Tab one fetch, one dimensional texture, okay, one dimensional array, okay. So this is the syntax, okay, and then put to the YM1, okay, okay. Read it, okay, and yeah, for the text new, okay, I read it from the YM1, okay. Oh, so my the battery, okay, yeah, it's not enough. Okay. Okay. So let me go to the code. Okay, let me go to the code. I hope I have still the connection is still there. Okay, yeah. Maybe I should connect to the battery first. Okay. Okay. Can you see me? Yeah. Let me see. Yeah. Okay. Let me go to code. The terminal is very sluggish. So okay. It's so yeah. Okay. Okay, here you see the kernel here. The kernel. Let me set the number. Okay, so set the the terminal is very slow. Okay, so